Okay, good morning. So let us now start the lesson. So we want to continue our journey towards this Euclidean geometry by completing a little bit, but I will teach only half an hour because we have the hour for half an hour, then we move to the 34. So if you remember, we talked about Circum Circle. And by the way, I mentioned it circumference circle, which was wrong, and I edited in the video. So if you remember, if I have any triangle, ABC say, and then there is a circle that passes through these three corners simultaneously, and that is called circum circle, yes? For that, you realize I wanted to demonstrate somehow by GeoGebra, just randomly drawing that circle will not work. Yes, you need to have a systematic way of thinking about how to draw that one. So do you remember what was that? I want to draw a circle that passes through these three corners simultaneously, which is called the circum circle. Yes? So what should I do first? Do you remember? You're studying Math 5 probably now, yes? Yeah, but it would be finished so early. Okay, so you remember I need to draw the perpendicular bisector, for example, here, and then perpendicular bisector here. The third one will also pass through the same point. We showed that, yes? So I put the needle of the compass here and open it here. Then automatically it passes through this point and that point, yes? Of course, this is easy, not easy to do it by hand, but anyway. So if I do that, this will give me a circle that passes through all these 3 points simultaneously, and that is called the circum circle. Is that right or not, the spelling? Circum circle, is that right? Might be this is a U. So let me check the spelling. Yeah, so that's a U. Okay. Now, do you remember I gave you a problem? I don't know how many of you start thinking about that. We want to show that if I multiply the length of each one of these sides together, then it becomes 4 times R times S. And I told you that this is a standard. The capital R is reserved for the radius of the circumcircle, and S of course is the surface area of the triangle, and ABC are the length of these sides. Okay? But before doing that, do you remember we learned a little bit about the Sine Rule when we were doing Math 3C? Do you remember the Sine Rule? It was also very interesting. So if you have any triangle, it doesn't matter which side and the angle opposite to which side you choose. If you calculate this ratio, if you calculate the same ratio for the other pair, or if you calculate this or the last pair, all of them are equal. So that is called the Sine Rule. Yes, do you remember that? So that is the Sine Rule. So let me, now, today we want to answer probably that what is this number? Can we say that this is, of course we know that this is equal to that, this is equal to this, we showed this. If you remember, if you want to go and back and review this, we found this formula using the area rule. And what was area rule? That's also good to know. If I have any triangle ABC, and I don't know, this is C, this is B, the area of the triangle can be written as 1/2 multiplying these two by the sine of the angle between these two. So that was the area rule, which is also a very important rule in geometry and trigonometry. So using this formula, we were able to show that these three fractions are exactly the same. But today we want to answer this question mark. Is there something that I can write for the question mark? The interesting thing is that this question mark, we want to answer this. It is exactly 2r. Yes? And this is equal to the diameter of this circum circle. Yes? We want to show this. So in Math 3C we knew up to here, but today we want to add one more equality, and that is 2r. r is the radius of this. 2 times r is the diameter of this actually circle. We want to show that this is true. Why is that? So, and then this is also reserved. This letter O is reserved for this point always. Yeah, it needs a little bit about circles. Of course, we have studied all of them in Math 2C, if I remember correctly. So let us try to use that. For example, let me draw this line. Let me take this one and connect it to this and continue it until it cuts the circum circle at some point, let us say E. Okay? Yeah. And then connect this E to A, for example. Yes? And now I ask you one question. So you should, in principle, you should be able to answer that. First of all, tell me, can I say something about the size of this angle? And if yes, why? So I connect this to the center and continued until it intersects the circumcircle at E, and then I connect it to A, and I'm asking you, do I know something about this angle now? So these are very standard famous ones you need to know. If you have a circle, I hope that you haven't forgotten this totally. So do you remember we had a central angle, the notion of a central angle, do you remember? The vertex is at the center and the sides are radii of this circle. So this is called a central angle. But we also have another type of angle, so that the vertex is on the circle and, for example, I don't know, for example, these sides are actually chords of the circle. This is called an inscribed angle. I don't know how many of you remember at least a little bit of this, yes? So we have two types of angle in a circle. The center is the vertex and the radii are the sides. This is a central angle, and this is called an inscribed angle. Do you remember there was a relationship between an inscribed angle and a central angle, yes? So what was that? If I have this scenario, if I have a central angle opening to this is, by the way, called the arc subtended by this central angle theta. Okay, and then let me take another angle, this one inscribed angle, but subtending the same arc. Do you understand? So this is an inscribed angle subtending this arc, and this is the central angle subtending the same arc. There was a very nice relation between the sizes of these two angles. Do you remember what was that? No? Do you know?
It's
Alpha is half of the theta. So yes, So theta is 2 times larger than alpha. It's extremely important theorem in Euclidean. This is one of those few important things that you have studied but you have forgotten, okay? So be careful about that. So if I have two angles, one inscribed one, the other one central one, but both of them subtend the same arc. If this is true, then the sizes of these two are related to using a very nice relation, a simple one. Yes? So the inscribed one is half of the central one. Yes? Okay, now let me ask you another thing. So here, now if I have a circle, I draw a diameter of the circle. This is the center. And then I choose any random point on this semicircle, say this one. And then I connect it here, and I connect it there. Then I know what that angle is. What is that? Yes?
90.
It's 90. It's very, very important. So the inscribed angle subtending half a circle is what? Is 90 degrees. Why? Because what is this angle? Definitely 180. And this is a central angle because its vertex is the center and its legs are actually radii. But we know that this is 180. And if I ask you what is the arc subtended by this, you show me this. This is the arc, yes, subtended by this. And exactly this is the same arc subtended with this. Yes? So this should be half of that one. So if this is 180, this has to be 90. Yes? So remember, this is an important fact. If you sit down on a circle and look at the diameter, the angle, the view angle is 90 degrees always. It doesn't matter. If I start from here looking the diameter, this angle is also 90. So it doesn't matter. Yes? Now, I hope that now you agree this is also 90. Yes, because this is the diameter and this is angle subtending this arc. So this is 90. Yes, but what is the relation between this angle and that angle? They are the same because both of them are inscribed and subtending the same arc. So each one of them is half of the size of the central angle. So it means that they are equal themselves. Yes? So now if I ask you what is sine of C, you can tell me this is sine of E because essentially E and C are equal. So I can conclude that the sines are also equal. Yes? But the point is that this triangle is a right angle triangle. Yes, this triangle is a right angle triangle. Sine of an angle is equal to the opposite side divided by the hypotenuse. Yes. So the opposite side is AB, which in geometry we agreed that show it with little c. So this becomes C divided by BE. But BE is the diameter of this, which is 2r. So very simple. So, and then I can interchange these two, yes? So I put 2r on top, and I put sine C down. So this becomes this one. But we already showed that these are the same. So if one of them is equal to this, all of them are the same. Yes? So that's a very nice relation. So far, you knew about this, but now you'll learn something more. So, and then, of course, if you want to, you can write A as 2r sine A. That's also a nice relation. The size of any side of the triangle is the diameter of the circumcircle multiplied by the sine of the angle opposite to it. Yes? Then this becomes this. This becomes this. It's good to know about these rules. Okay? Of course, might be I was actually going very ahead asking you to prove this, but now proving this is not that hard, yes? So we can start from the right-hand side and show that this is indeed the case. so I want to start from the right hand side, which is 4RS. And let us see what can we write here. Okay, you see it is still on the board. Instead of S, I can use this area rule formula, which you learned in Math 3C. So this becomes 4 times R multiplied by, instead of S, I put 1 over 2 BC sine of A. Agree? But now what happens, this 2 and this 2 will cancel. So this 2 and this 4, it becomes 2R. And if you don't mind, let me write sine A next to it. And then what I have BC left alone. But what can I write instead of this? It's A. That's ABC, yes? So this becomes ABC, which is equal to the left hand side. So this is a formula. So if someone asks you, if I give you the length of these triangle, can you calculate the radius of the circumcircle? You would say yes. Why? Because R is equal to this one, ABC, divided by 4S. Yes? But if I give you the size of these sides, the numerator is the product of those numbers, and this S, you can use the Heron's formula, yes? Because if you know ABC, you can immediately calculate S, so, and then you can calculate this, R is found, yes? So this is something that is important to know. Okay, so that is an extra piece of information, but a useful one. So I don't know how much time we have. We have a little bit more. So I want to teach you one theorem that is called Ceva's theorem. Ceva's theorem. But the consequence of this would be for the next session. Okay, so Ceva's theorem is this. So do you remember what was the definition of a Cevian line? What was a Cevian line? You have a triangle. You take a point here, and then take and connect this vertex to this. This would be a Cevian line. Yes? Now consider 3 Cevian lines, one from here, and the other from there, so that they are concurrent. All of them are passing through the same point. So for example, I can take this one, let me call it Y. I will take from here to here. Of course, I can draw another Cevian line from here, which does not pass through this one. Ceva's theorem is not about that. Ceva's theorem is talking about what happens if I have 3 concurrent Cevian lines. Yes? So the third one, I myself intentionally draw it from here. Yes? Okay? And then let me call this one Z. So is it clear? So I have 3 concurrent Cevian lines. Yes? The Ceva's theorem tells you that if you measure Bx from here to here and then divide it by xc, and then you measure from c to y and then divide it by y over a, and then you measure az in a circular way, you see, and then divide it by zb, and then multiply these 3 numbers. This is always exactly equal to 1. Okay? So that's a very, very nice theorem. So if you take bx over xc multiplied by cy over yz multiplied by az over zb, this is exactly equal to 1 no matter how you draw them. So the only thing that you need to respect, you need to have 3 concurrent Cevian lines. In that case, this will work, yes? And the proof is actually very nice. I don't know if we have time for this, but at least we can start. If it is left, we can keep it for the next time. So do you have any idea, at least we can discuss, if you want to prove such a theorem, what is probably the good starting point? Before doing that, let me remind you of something. If A over B is equal to C over D, do you remember I talked a little bit about non-trivial operations that you can do with these proportionality equations, yes? So for example, do you believe in that if this is the case, do you think that I can write A over B is equal to A plus C, B plus D? Is it reasonable for you or not? So do you remember I told you that if you have A1 over B1, A2 over B2, up to, and all of them are equal to some number K, if you want to, you can multiply the first number by alpha 1, you can multiply the second number by alpha 2, and then you can continue. And whatever you did for the numerators, you do exactly for the denominators. So for example, alpha 1 B1, and then you have alpha 2 B2, and then you continue. If you add these, this also becomes K. You remember we had something like this. It's a very non-trivial, it's not hard, but it is not that trivial in the beginning. So if I have a set of fractions equal together, if I start multiplying the fractions by different numbers and adding them, and whatever I had done for the numerators, I do with the denominators, and then I will make a new fraction, but the value of the new fraction is exactly the value of the previous fractions. So for example, if it's clear that 2 over 4 is 3 over 6. Do you agree? Yes? Now let me multiply this by 5. Multiply this by 7. Yes? And I do the same thing here. Multiply this by 5. Multiply this by 7. Add these two. Yes? Let us see what happens. This becomes 10 plus 21. This becomes 20 plus 42. The numerator is 31. The denominator is 62. But 31 over 62 is 2 over 4 again. So is that understandable? Yes or no? So in general, I can write this as well. So it means that I have chosen alpha 1 equal to 1, alpha 2 equal to 1, and then I got this. Yes? And I can do the same thing. If A over B is equal to C over D, can I conclude that A over B is A minus C, B minus D? Yes, this time I choose alpha 1 equals to 1, but alpha 2 is chosen to be equal to minus 1. Yes? So these are very interesting and non-trivial things that you can do with these fractions that are equal. Yes, this is something that I want, let us keep one of them that is necessary here on the board. Okay, let me write something because these theorems that usually carries a name, they are a little bit hard. Okay, so let me write something, then I ask you, do you agree with me or not? So for example, if I write bx over xc is equal to the area, let me give this a name. For example, let me call it M. If I write it as the area of the triangle AMBX divided by the area of the triangle MCX, do you agree with me or not? These little pieces you should be able to discover and confirm. Do you agree that this is true? This length divided by this length, I am claiming it is equal to the ratio of this area to this area. Yes, is that understandable or not? If yes, why? Yes?
Is it not because the height is
The heights are the same, yes? Because if I ask you, what is the height of this triangle, you draw this one. But the same line plays the role of the height of this one as well. Yes? Yes, because I have a triangle like this. If I ask you to draw the height to this one, of course you draw this one. But if I ask you to draw the height to this one, you have to continue it in your head and draw this one. Is that understandable or not? So that height, which is the height of this triangle, is also the height of the same triangle here. So if I ask you, what can I write for this one? So for this one, you can write 1 over 2. Let me call the height h. You can write 1 over 2 times h times bx. And for this one, you can write 1 over 2, the same height, but xc. Agree? And when I divide this by that, of course, this one and that one are gone. And I get this fraction bx over x. Is that understandable? So if you look, you need to train your eyes to catch these figures and details. Okay, so let me just clean that one. Now you understand why this is true. Yes or no? Okay. Now, I write it this another way, but I want you to exactly tell me why. So this one, on the one hand is this, on the other hand is this area. Area of B, M, B, no, sorry, ABX. ABX divided by the area of CX. Is that understandable? Yes, that's the same idea, yes? But this time, just clean this one and concentrate this triangle with that triangle. Actually, exactly the same theorem, yes? But this time you need to imagine that you are drawing this height. This triangle, yes? And this triangle, yes? Is that understandable? So that is also true. Yes or no? But now let me, from these two, I want to write this. I want to write this. Yes, I want to claim that if this is true and this is true, I hope that you agree with me, both of them are true, I can conclude that the same fraction is also equal to this. Why is that? This is not trivial. You see, this was more or less I used the same concept, the same idea for here and here. But now I am claiming that if this is true and this is true, this one also becomes equal to the ratio of these two triangles. Why is that? Okay, do you see that or not? So it means that if I have one fraction equals to two different fractions, if I subtract the numerators and I subtract the denominators, it remains the same fraction. Yes or no? So I start subtracting them. So it becomes S of ABX minus S MBX. And I will do the same thing for the denominators. So S ACX minus S MCX. So is this line understandable? So I was able to show this one is equal to this one is equal to this one. So it means that these two fractions are equal. Why? Because both of them are equal to the same thing. Now, if I subtract the numerators and I do the same thing for the denominators, I get a new fraction. But this fraction, according to what I showed there, is equal to the previous fraction. So the subtraction is equal to this one, on the one hand. On the other hand, look at the figure. What is the s of this minus s of this? It's exactly s of that. Yes? S of a bx is from here to here. This is a bx. And SMBX is from here to here. I take it away. What is left is this area. Yes? So that is area SMAB. And for the same thing happens here. Yes? So we learned that BX over XC is actually S of MAB, SMAC. Yes? But now I want you to use your intuition. You have to repeat this process two more times, yes? One for this side, one for this side, one for that side. But it is not hard to imagine what will happen. Can you tell me what will happen for the other fraction? So let me clean this one. So what will happen for the other two fractions? So let me put this in a box. I will need it for the future. But can you tell me, if I want to do the same thing, what will happen for Cy over Ya? And what will happen for AZ over ZB? What will happen here? So Bx over Xc, at the end, this triangle was important and this triangle was important. Yes? But now look at the problem from this side. Can you tell me which triangles would be important? Yes, it's a little bit confusing. Yes?
MBX and
MBX, no, MBA, I agree with that.
Oh, MBC.
So yeah, one more. So maybe please. So here, see what if you look at from this perspective, it should be MBA. Yes. Sorry. Which one? By the way, which one is which is very important because BX and XC, you have these two in front. So BX, the triangle on top of that is this one. So we wrote it on top. And then CX is this one, the triangle on top of that is this one, so we wrote it in bottom, yes? Now we go back here and CY over YA. So what is CY over YA? I can write it as triangle what? MBC. Yes? And then over AMB. Yes, I want you to convince yourself. Is that right? If you look from that angle, yes? Otherwise, if you don't believe, you have to repeat this process 2 more times. And then what happens for this last chance? Can you read this one? AZ over ZB is what? Yes, MAC divided by? Yes? I am finished. Yeah, 1 minute. Huh? Yes, I am finished in 1 minute. Yes.
1 minute?
Yeah, yes.
MCB.
MCB, yes? Agree? Now we start multiplying these 3. So what happens? This is in the numerator. When you multiply, it will cancel this one in the denominator. This one is in the denominator, will cancel this one in the numerator. And this one in the numerator cancel this one in the denominator. When you multiply them, it becomes 1. Yes? So it was a little bit unusual. So these people were actually very creative in proving these theorems. And of course, we knew we want to prove this. You have to invent this relation and then prove it. So you have to be very creative. Okay, thank you very much. We go to 34 and then you can relax now.